all of you for coming to celebrate Carlos' birthday, but it's the last day of the activities. We're going to have two talks. The first one by David Torres. David was our colleague here in PUC, and now he is in Universidad, Politécnica de Madrid, in Madrid, in Spain. Okay. And David is going to talk to us about integrable systems and Poisson geometry of compact type.
Okay. Thank you very much, Nicolau, for the introduction. Well, thank you very much to all of you for being here on Friday. Last day of a conference actually requires some energy to wake up and come to the venue. So, the first thing that I like to do is to congratulate the organizers of the conference. I think they did a great job. I am only partially aware of how much they worked because I was in this mailing list, exchanging some emails, and I could basically check the amount of things that were going on, and I can only imagine what happens here locally. I mean, that they basically spend lots and lots of time. So they made a great job. Now, as far as Carlos, so I made Carlos' acquaintance quite late in terms of people here that know him since a long time. So we met in 2014 when I came to work to PUC. And what I encountered was a youngster, because I think that describes Carlos very well. I mean, he's a person that he's very passionate. I mean, he has lots of will to learn, and whenever he learns anything, he wants to share it with people. I mean, no matter whether it's in the elevator, in the coffee room, I mean, anywhere. And it's not only that. I mean, he's also very, very positive. I think Peter talked about that. I mean, he always sees the positive things positive side of things. And when you are in a math department and you basically work with people and see people on a daily basis, it is great to have a colleague like Carlos, because I mean, it really cheers you up and makes life easier in the department. And in that sense, I think that PUC, and especially the math department, is really fortunate for having had you for many years and still having you here. So, and I hope that lasts much longer.
Professor.
Now, I should also say something about how Carlos and I work. I think that when I arrived to PUC for around a couple of years, we had some casual math discussions, but we never talked math seriously. It was just, exchanges of opinions. And at some point, I think in 2016, I don't remember exactly when, and I don't remember how, we started collaborating in, guess what? One of the subjects that Percy says that every mathematician in her life or his life has to encounter at least once, in the Toda flow. So we started working in the Toda flow, and it's very interesting how our working sessions go. Because if you want to work with Carlos, the first thing that you have to do is lock him in a seminar. And that's not meant to be a metaphor. I mean, you have to go to the 7th floor and lock yourself with Carlos inside, because he's a very busy person. There will be staff coming, there will be students coming, and you have to have him under key. Now, I don't know whether you've been in the 7th floor, but I mean, the seminar there is very nice. It's a very narrow seminar, but I mean, both long walls, they are covered by blackboards. And our sessions invariably would start in the following way. So we would enter the seminar. Some of us would go to one of the blackboards and write a square table of scalars. Now, what is that? Well, depending on who each of us is looking at it. I mean, if Carlos looks at that, he sees a matrix. And you can ask anything you want about matrix calculus, and Carlos will have the answer. So it's exceptional. However, when I look at the table, I don't quite see matrices, I'm afraid. I see Lie algebra elements, and sometimes Lie group elements. So we speak a totally different language, but there's enough common ground so we can actually talk to each other and end up learning from each other. And I think the process is quite fun. And I think that's reason enough to have it going on for as long as possible. Okay, about the topic of the talk. So it's integrable systems and Poisson geometry of compact type. I don't have a slide when I'm going to explain to you exactly what I'm going to be doing during the talk, because it's a little bit complicated. But the underlying idea is that we want to use Poisson geometry to detect those integrable systems which will be non-regular, but which have the simplest singularities possible. That's the idea. And it's joint work in progress with my collaborators, my colleagues, Marius Crainic and Fernandes. All right, so let me start with an example of a complete integral system. It's I put periodic total lattice. Well, it should be non-periodic, but it's just the first example. The work of Henon and Flashka was both valid for the periodic and non-periodic total lattice. So remember that a complete integral system, well, what you have is a symplectic manifold. Classically, it would be phase space, R2n with position and momenta, but in general, it's nonlinear, so you have a symplectic manifold. And typically, you're given a Hamiltonian vector field whose trajectories you want to study, and not only trajectories, maybe global behavior, global dynamical behavior. And what you do is you try to that Hamiltonian vector field, add up more functions that are in Poisson, that Poisson commute with it, as much as half of the dimension of the symplectic manifold. If you manage to do that, and the functions are functionally independent almost everywhere, then you have a complete integrable system. Now, the first example is the total vector field. Well, in the case of Henon, in the phase space that Toda originally introduced. In the case of Flashka, is in his coordinates in Jacobian matrices. The second example is still the Toda vector field, but now what you do is basically enlarge the phase space. Now you work with regular orbits in symmetric matrices with fixed spectrum. Those are symplectic manifolds, because you can actually decompose matrices in two different ways. You can do symmetric plus antisymmetric, or you can do symmetric plus upper triangular. And that decomposition, what does is identifying the dual of the symmetric matrices with, the symmetric matrices or the dual with the dual of the upper triangular. Now, symmetric matrices, algebraically, they are not very interesting. They are a module with respect to the antisymmetric, but the upper triangular ones, they are a Lie algebra. So what you're basically putting is a linear Poisson structure in symmetric matrices. Hence, in the corresponding orbits, you have symplectic structures. So that's the phase space. I should also mention the names of Geckman and Shapiro, because, I mean, what Dave, Lee, Nan, and Tomei did in the case of symmetric matrices for the simple algebra AN, so they did in the general case for every simple Lie algebra. And the last example is still the Toda vector field, but in a larger phase space. Now, essentially, you remove the symmetry condition, and you look at regular orbits. The symplectic geometry, or the Poisson geometry here, is much more subtle. We heard a little bit about that in the first talk of the conference, because you have to use a different multiplication, a different group structure, and that actually brings a Lie Poisson structure that plays a role. So here, the symplectic structure is much more subtle, much more interesting. All right, so when you have a complete integrable system, typically what you want is, like I said, understand or say things about the given vector field, Hamiltonian vector field. In this case, the Toda vector field. Compute trajectories by quadratures and, discuss more conditions. And the singularities or the zeros of the vector field are going to be reflected also in the singularities of the complete integrable system. Now, what I want to do in this talk essentially is try to get rid of those possible singularities as much as I can. And I don't want to do it in the case of complete integrable systems, because things are rather well understood in that case. I want to be a little bit more general and do it for the so-called non-commutative integrable systems. So what is a non-commutative integrable system? You start with your symplectic manifold, and now you give a family of functions whose number is above half of the dimension of the symplectic manifold. You're going to call the rank of the system the difference between 2n and the number of functions. So this rank R, it's used to basically split your functions into blocks. You take the first R functions, and then the rest of the functions. And then the involutivity condition that you place is not symmetric. So you're saying that each of the first R functions Poisson commute with the other ones. And then you have the usual independence condition, right? Now, well, examples, of course, we are generalizing the usual integral systems. These are the systems of maximal rank, like the Toda system. The second third and fourth example are there. I mean, I don't do dynamics, but it's simply for you to realize that this is not an invention of mathematicians. And so there are many interesting systems that do not fit. They are not completely integrable, but they are integrable in the non-commutative sense. For instance, the Kepler problem is a non-commutative integral system of rank 1. If you put some additional topological conditions, these superintegral systems, they will have periodic trajectories. Okay. Second and third examples, these are non-commutative integral systems in symplectic manifolds of dimension 6 in cotangent bundles. They have rank 2, so it means that you're going to have 4 functions, 4 Hamiltonians. The 2 of them are the more important ones, and then you have 2 additional functions. And the last example is also an example of mathematical nature, is the Gelfand cycling system, but it's so important that whenever you can mention it, you have to throw it in the talk. And, well, why would you care? I mean, why people introduce this notion? I mean, I should say that these were introduced by Mishenko, Fomenko, Nekrasov. And, well, if you have a Hamiltonian vector field, the one that comes from F1 that fits into a non-commutative integrable system, you can compute the trajectories by quadratures. So this has a very clear objective. Okay? All right. So what I want to do is slowly shift in my attention from non-commutative integral systems to Poisson geometry, or if you want, bring in Poisson geometry into the picture as much as possible. And for that, I'm going to assume that my non-commutative integral system has no singularities, or at least I'm going to work in the regular part of the system. So I'll do the following thing. I'll take all the functions and produce a map to RK. That's the moment map. And this function has very interesting properties. If you take a regular value, the corresponding fiber is going to be a submanifold of X, and it happens to be isotropic. That's a very standard property. More interestingly, if you look at the distribution given by the fibers and you take the symplectic orthogonal, since this is an isotropic distribution, you get something which is coisotropic. And more importantly, that distribution is integrable, gives you a foliation. And now you can play the usual game, reduction game in symplectic geometry. You have a coisotropic submanifold, you quotient by the kernel of the symplectic form. If what you get is a manifold, then it's a symplectic manifold. Well, in this case, if the fibers are connected, it is, and you're producing a symplectic manifold, which is actually a symplectic leaf of a Poisson structure in RK. That's what you're doing, really. Okay? If you want to look at this just using functions, the leaves of this large foliation, they are simply the values of the first R functions. And the fibers, of course, they are the values of the entire moment map P. Okay? Right. Well, what I would like to do is take this picture, this non-commutative integral system without singularities, and basically introduce a more geometric perspective. So let me just use the following name, abstract regular non-commutative integral system. So what is that? Well, it's so perhaps before the definition, I forgot to say something about this, is that when you have this map, when you introduce this Poisson structure, the brackets, the Poisson brackets here, and the brackets that come from the symplectic structure here, they talk well to each other. So this is a Poisson map in the following sense. If you take a couple of functions here, they compute the bracket and pull the result back, is the same thing as pulling back the functions, computing the bracket here. Okay? And that means that if you would be interested in doing Poisson geometry here, what you actually should do is pull back your problems in Poisson geometry to problems here, because this is a symplectic guy. And we know to do things much better when the brackets are non-degenerate. Okay? All right, so what is an abstract and regular non-commutative integral system? You have a symplectic manifold, you have a Poisson manifold, and you have a Poisson map, which is submersive. And you ask the fibers to be isotropic. Okay? And the rank is the dimension of the fiber. And in this talk, my fibers are always going to be connected. I don't want to get into connectivity problems. And from the definition, I mean, you see that the Poisson structure that you have in the base has to be automatically regular. Okay? Now, I gave here 2 different names, abstract regular non-commutative integral system, and then isotropic submersion or isotropic realization. And that actually depends on the viewpoint that you want to adopt. If you're thinking about the integral systems, well, that's something that gives you locally many integral systems. in the following way. So there you have a picture of a isotropic Poisson submersion. So you have your symplectic manifold. You can think that this box is dimension 4. What you have down here is supposed to be dimension 3. And these are symplectic leaves, that they should be surfaces, which we cannot quite picture. So you have here the fibers that are one-dimensional. So how do you recover the classical, the ordinary non-commutative integral system from the picture? So you need it. So if this is dimension 4 and this is rank 1, I need to give you 3 functions. The first one in involution with the second and the third. So what is the first function? Well, you get them here locally. What you have to do basically is take a Casimir of the Poisson structure down here, and a Casimir in principle is going to be a local function. If you're lucky enough, you will have global Casimirs, but that's typically not the case. You take a Casimir, and then you take 2 more additional functions that give you a local coordinate system. You have your 3 functions down here, you pull them back by p. That's the non-commutative integral system. So this abstract version basically it's a coordinate-free version of a regular non-commutative integral system. So there are no singularities whatsoever here. Or if you want, all the flows that you get, they are linearly independent. So why I'm, again, using the name isotropic realization? So that's the name that you would find if you look papers in Poisson geometry, because, again, one shifts the viewpoint. In this situation, the Poisson geometry here is important. You want to study it, and you pull back problems up to the symplectic structure. So this is meant to be a symplectic desingularization of the Poisson brackets here. You have here non-degenerate Poisson brackets, and you have here an object that has, degenerate Poisson brackets, and here non-degenerate Poisson brackets. You pay a price because you have to enlarge the dimension. But here, in this situation, you pay the minimal price because you see, here you have like one dimension that is non-symplectic. And it really wants to be paired up with another guy to give you a symplectic form. And that comes from up here. So you're actually putting a guy that has minimal dimension to be a symplectic resolution. There are instances in Poisson geometry where you have this kind of symplectic desingularization that have much larger dimensions. So this one is optimal in the sense that it has minimal dimension. It tells apart, selects very nice Poisson manifolds in that way. Anyway, so I'd like to remind you some global properties of non-commutative, commutative, and non-commutative integral systems without singularities. And to be able to do a little bit of global Poisson, a little bit of global geometry, I need to impose some topological condition. And that topological condition is that the fibers of the map P be proper. That the map be proper, the fibers be compact. Okay? So what do we know in the classical case? So in the classical case, what do we have? A proper Lagrangian fibration. Is a Lagrangian fibration? Yes. It's okay. The name superintegral, I know that it's used when the non-commutative integral system has one-dimensional fibers, when the rank is 1. It may be also called in his papers, which I never read, I have to confess, also superintegral. But I assume it's the same notion. Yeah, so he calls them superintegral if they go above half generically. That's okay. So we're using here non-commutative for in that case. Okay. All right. So what do you have if you have a proper Lagrangian fibration? A Lagrangian fibration with compact connected fibers. Well, first very important thing. The base cannot be an arbitrary manifold. We'll review this later in more detail. It has to have an integrally defined structure. And that's very, very demanding. For instance, if your manifold B is an orientable surface, it can only be a torus. So no other orientable surface admits an integrally defined structure. We have action angle variables, which in principle are semi-local. And then you can ask global questions. So are the action angle variables global? Or rather, are the angle variables global? And there's an abstraction class introduced by Duistermaat, this Lagrangian Chern class, whose vanishing is equivalent to the existence of global angle coordinates. And you can also ask more questions of global nature. If I give you this manifold B with an integrally defined structure, so it's a candidate to be the base of a proper Lagrangian fibration, does it have 1 on top? The answer is yes. How many does it have up to the natural notion of equivalence? Well, as much as elements in the corresponding cohomology group. So these questions are completely solved in this situation. Okay, let's generalize and let's go from commutative to non-commutative. So what we have is a proper isotropic fibration. Again, it's a Poisson map whose fibers are compact and connected, and they are isotropic. Now, there's a parallel theory here that was done by Dazord and Delzant. And essentially, they tell you the next thing. You see, the base now is a regular Poisson manifold. And what it has is the analog of an integral affine structure. So it has a transverse integral affine structure to the foliation. What's the meaning of that? If the foliation had a smooth leaf space, it would be an integral affine structure on the leaf space. It's just that, in general, foliations can be very badly behaved, and you make sense of what would be a geometric structure in the base by means of a transverse geometric structure to the foliation. And Dazord and Delzant, they also introduce an obstruction class to the existence of one of these proper isotropic fibrations on top of a given foliated or regular Poisson manifold with a transverse integral affine foliation. If this class vanishes, then you do have one of those guys on top. And you can say how many you have as well. Okay, so what I would like to do in this talk, and I'm slowly going, trying to explain what I want to do, is given a Poisson manifold, now non-regular, plus an analog of a transverse integral affine structure to the foliation, and that's delicate because when the manifold is non-regular, you don't have a foliation, you have a singular foliation. The dimensions of the leaves vary. What is a non-commutative integrable system? If I have one, the map P, it must have singularities because the Poisson structure here is non-regular. It's forced to have singularities, but what are the simplest singularities? What are the non-commutative integral systems that possess the simplest singularities? These would be like the closest analogs to these guys for non-regular Poisson manifolds. And if they exist, is there an abstraction class? Can they be classified? So what I'll try to do in the rest of the talk is try to, well, maybe not convince you, but simply telling you what's our proposal for this kind of non-commutative integral systems with the simplest singularities. And let me try to summarize the objective of the talk in a picture. Okay, so the starting point is one of these proper isotropic fibrations of Dazord and Delzant, generalization of proper Lagrangian fibrations. We have a regular Poisson manifold with a transverse integral affine structure. Now, if I want to generalize this to the world of non-regular Poisson manifolds, at least the way we work is that we really have to impose some conditions on the foliation of the regular Poisson structure. I mean, things can get very complicated if we don't put constraints. So we're going to ask the foliation to be nice.
Can you clarify one thing? When you say regular, do it just means that the non-regular? Yeah, it just means that the rank is not constant.
Exactly. It's not a submersion. Yeah, yeah.
So in the case of total, also there are many, leaves of different dimensions.
Yeah. So if
why do you call that case regular?
No, I'm calling because I'm thinking about toda on individual leaves. So typically, when you restrict to a leaf, that's the way that I thought in the introduction about toda. But I mean, if I want, and it's the same for Gelfand cycling. I mean, it's a little bit more subtle because, for instance, if you go to Gelfand cycling, you can introduce the notion of the analog of a non-commutative integral system when the total space is not just a symplectic manifold, but you can allow also Poisson manifolds. And with Gelfand cycling, if you want to treat all orbits at the same time, you have to go to this more general version in which this is a Poisson manifold. I'm not sure about toda because I didn't think about that, but
for toda, it's just a leaf Poisson structure, but there are different kinds of leaves, right?
Mm-hmm.
So you can consider total lattice. So that's kind of leaf as minimal dimension, right? Mm-hmm. And then you can consider generic leaves, and those are of maximum dimension.
Yes.
So in that sense, it's also non-regular. Right?
It is non-regular if I put all the orbits together, and it's not the one of the guys that I would like to treat because when I go to regular orbits, toda has singularities, has zeros. So the corresponding commutative integral system wouldn't give me a Lagrangian fibration. Will give me something that has singularities. And that I don't want. I want to be in the simplest case. I want to avoid singularities as much as possible. So toda wouldn't illustrate what I'm going to do here. It served the purpose at the very beginning to recall what the commutative system is, and also to cite some people in the audience. But now I'm moving to things that are much simpler. Okay, so I have this non-commutative integral system, which is regular and has a very nice foliation. Well, that's an example of what we call a Poisson manifold of compact type, a regular one. Now, these Poisson manifolds of compact type, if you are given one, they have the very nice property that the leaf space, it's an orbifold. It's almost a manifold, and it also carries a transverse integral affine structure. So these are good candidates to have on top of them this kind of proper isotropic realizations. I'm not giving you, and I'm not sure I'm going to give you the definition of what this guy is, but the idea is that these Poisson manifolds, they also possess nice symplectic desingularizations. That would be the definition. And what you're asking is that, well, if I have one of these guys that has a nice Poisson symplectic desingularization, does it happen to have an optimal one in the sense that it's of minimal dimension? That would be a proper isotropic realization over your Poisson manifold of compact type, the regular one. Okay? Now, these Poisson manifolds of compact type, they need not be regular. We also have non-regular ones, and those are the ones over which we want to put elementary non-commutative integral systems. Now, these kind of Poisson manifolds, they have a very nice property, which is that even though they have non-regular Poisson or Hamiltonian foliations, these foliations, they can be resolved. You can inflate leaves that don't have maximal dimension and produce a manifold, produce a foliation which is regular. When you do this resolution, you pay a price, because if you pull back the Poisson structure, the structure that you get here gives you brackets, but not for all functions. This is a Dirac structure. It's a generalization of Poisson structure. Now, our proposal is to place what we call a proper multiplicity-free realization. And that name multiplicity-free maybe should ring a bell for people doing Hamiltonian actions. And these nice non-commutative integral systems will have removal singularities in the following sense. We will be able to basically resolve this Poisson map into a Poisson map that is a submersion. So we will get rid completely of singularities. Again, price to pay. The brackets here and here, they are a little bit degenerate. So this won't be a symplectic form. It will be a possibly, or it will have kernel. Still, in this setting, many of the things that you do in the symplectic Poisson case still work. So this is a desingularization of the map that produces singularities on the geometric structures. There's a price to pay, but the singularities are mild enough that allow you to do Poisson symplectic geometry. Okay? Right. Okay, I took half of my time just to try to explain you what I want to do.
What is MCT?
Sorry?
MCT and so on.
What is?
MCT.
Oh, it's a Dirac manifold of compact type. So PMCT is a Poisson manifold of compact type. It's a very nice Dirac manifold, and it's regular. All right, so what I want to do is very carefully reviews the classical construction of action angle coordinates that I guess most of the people here know, but I want to emphasize the role of integral affine geometry because it will be very important in what comes next. Okay, so this is a dimension 4 Lagrangian fibration over a two-dimensional base, right? It's proper, so the fibers are compact. Start building action angle coordinates. Pick a point and look at the corresponding fiber. Now, this arrow here is dashed because if you see a non-dashed arrow, you're going to think that that's a vector. And that's supposed to be a covector, right? I don't know how to paint covectors, so that's my convention. So you pick a covector at that point, and you pull it back by the submersion. It gives you a covector that you can place at any point in the fiber. Use the symplectic form to turn it into a vector. Because the fibers are isotropic, the vector is tangent to the fibers. So what you got is a vector field. If you do that for another covector, you get another vector field, and the vector fields are commuting. If you place the condition that these two vector fields are complete, then your fiber has like very few possibilities. Either it's an affine plane or it is a quotient. So that is an annulus or torus. If you are saying that the fibers are compact, you know that these are torus. Okay? So you know that you have individual tori over each point. And also, what you're going to do is for each point, you're going to mark those points whose associated flows in the fiber are the identity. Right? And that's going to give you a two-dimensional lattice in this two-dimensional vector space or covector space, right? And you're going to choose at each point a basis of the lattice, these two guys. Now, if you take nearby points, of course, you can take a smooth basis. And if any element of the basis, when you move it to nearby points is giving you a one form, right? The important property, the key property of those one forms is that their graphs are Lagrangian inside of the cotangent bundle. And there's a very classical theorem of Weinstein that tells you that if in the cotangent bundle you use the symplectic form, that's a tool to distinguish closed forms from non-closed forms. Closed forms are the ones whose graph is a Lagrangian. Okay, if the graph is a Lagrangian in a small neighborhood, these guys are d of a function x1, d of a second function x2. Those are the new coordinates here. And these are the generators of the lattice. So what you did is uniformizing the lattice. You make a nonlinear change of coordinates so that your lattice is constant. Well, that means that if you think of your base space as the dual of the Lie algebra of a torus, what you have here is a Hamiltonian action of a torus. So you build a local Hamiltonian action of a torus using integral affine geometry. Okay? So let me just, in the left-hand side, you have like the local consequences, and in the right-hand side, I put the global ones. Local consequences, like I said, we have a Hamiltonian T space. And again, if you remember your courses on Hamiltonian actions, that means that this map is a Poisson map for the Poisson structure that comes from the dual of the Lie algebra, which in this case is the zero Poisson structure. So locally, we have the zero Poisson structure. Second and third conditions, they are equivalent, but when we go to the more general case, we'll have to choose one of them. So the fibers, when you have a Hamiltonian action, typically the fibers are going to be isotropic, but they may not reach the dimension to be Lagrangian. And in this case, they are Lagrangian, which is to say they are coisotropic. So that's the special condition here. The fibers are coisotropic. And another equivalent condition is that the action of the torus is transitive on fibers, right? So the transitivity of the action and fibers being coisotropic are equivalent. Global consequences. Well, I told you that these coordinates, which are local, make you think of having the zero Poisson structure on the base. Well, that means that you have the zero Poisson structure everywhere in the base. So, second consequence, that's very, very important. Your manifold B is integral affine because, you constructed a chart that uniformizes the lattice. So using this chart, if you make a change of coordinates, the lattice has to go to the lattice. And the only possibility is that the diffeomorphism is an affine transformation, but not only that, because it has to preserve that lattice, the linear part, the matrix, has to be unimodular. So it's an integral affine transformation. It's a very, very rigid structure. Because, for instance, if you are in a affine space, in two-dimensional affine space, what are the affine submanifolds? They are affine lines that you can move smoothly. If you are in an integral affine two-dimensional space, what are the integral affine one-dimensional submanifolds? The lines that have rational slopes, and they are rigid. So this geometry is extremely rigid. It's hard to get, but then it pays off because it gives you many things.
The translations.
The translations, yeah, but you cannot change directions and the translations. What is the Duistermaat obstruction to having global action coordinate, to having a global action of a torus? I guess that you now understand very well, because you do the following thing. I take a point, and I look at the basis that I chose. I take a loop around my manifold, and see how that basis changes. That loop is going to give me a transformation, a linear transformation with integral coefficients. But you see, this kind of a structure in the base, if you want, is real analytic. If you take a loop and you perturb it a little bit, what you get when you go around doesn't change. So this is an invariant of the pi1. So you're getting a map from pi1 to, in this case, the general linear group with integral coefficients. Well, modulo that is non-abelian cohomology, what you have to use, that's an element of H1. And this is the monodromy of the lattice. So having a global action is having a lattice with no monodromy, right? So that's the class of Duistermaat. All right, so this is what we want to generalize in a non-commutative situation, meaning the following. I told you that I'm going to do things over Poisson manifolds of compact type, blah, blah, blah. I'll go to the simplest case. I'm asking myself, if I'm given a linear Poisson structure, what is the simplest possible integral system with, again, very, very simple singularities? Okay, so it's going to be a Poisson map, which in principle, I will start putting conditions that mimic what we have in the Lagrangian case. And I simply wanted to remark here that having this is the same thing as having a Hamiltonian action of a Lie algebra. right? If you feel more comfortable in the Hamiltonian setting, don't think that this is a Poisson map from a symplectic to the linear Poisson structure. This is a Hamiltonian action of the Lie algebra. That's very important, just the Lie algebra. And if you want to see the equivalence, it's the same game that we played before. If you want to leave the action, take a covector here, which is a vector of the Lie algebra. That's a 1 form here. Pull it back, it's a 1 form. Use the symplectic form, it's a vector field. And that behaves with respect to brackets. Okay? Okay, this map is never submersive. It cannot be. That's if you want basic Hamiltonian actions, because this guy is non-abelian. So, challenge. Can we control the singularities of P's only imposing, I don't want to say, I want this type of singularity. I don't want to use singularity theory. I want to use just Poisson geometry conditions on the action of Poisson nature, and perhaps some differential topology restrictions on P. But I don't want to prescribe singularities. I want to do it in a different way so I get simple singularities. Okay, natural assumptions. You see, if this action of the Lie algebra can be integrated to the action of a compact Lie group, then we start to be in business. The reason being that when you have an action of a compact Lie group, you have a normal form theorem by Marley, Guillemin, and Stenberg that tells you how this map looks like. So it would give you a lot of control. So we would like to lift this Lie algebra action to a Lie group action. So the Lie algebra has to be of compact type because we want this group to be compact. So it will have center plus semi-simple part. Mimicking the conditions that we have in the Lagrangian situation. In the Lagrangian situation, the Lie algebra acted transitivity on the fibers. In this nonlinear case, well, when you look at the coadjoint action of the Lie algebra, of course, it moves coadjoint orbits. But if you fix a point, the corresponding isotropy Lie algebra acts on the fiber. So you want the isotropy Lie algebras to act transitively on fibers. So that's a multiplicity-free condition that we want to impose. And we want P to be proper, right? Note the following thing. The moment that you throw in the properness property, these vector fields of the action, they are complete. So the Lie algebra action integrates into a Lie group action. The problem is that that integration is in principle valid for the one connected into the largest Lie group with this Lie algebra. And if you have center, this Lie group is non-compact. So you do have a group action there, but the group is non-compact, so you cannot use slice theorems or anything like that. So that's not a tool so far. Okay, so we're moving towards multiplicity-free Hamiltonian G spaces, so-called also Gelfand pairs. So I'm going to assume that indeed I was able to lift the Lie algebra action to a Lie group action of a compact group. And let's see what do we get. So I have a Hamiltonian G space, my group is compact and connected, and I have this property which is equivalent to the multiplicity-free condition. When I pull back a coadjoint orbit, that's exactly an orbit of the group G. And that means the following thing. I mean, if this value was regular, I could perform Hamiltonian reduction. I would take the preimage of the orbit, and I would quotient by the action of G, and that would give me a symplectic manifold. If the action is transitive, I'm getting a point. So this multiplicity-free condition means that the reduced spaces are points. Okay, so I'm going to look at the central fiber, and I'm going to pick a point in the central fiber. Because the action is transitive, the central fiber is a homogeneous space. It's G mod K, the stabilizer of that point, right? And the fiber is also Lagrangian. So I can use Weinstein's theorem to see that in a neighborhood of the origin, my guy is the cotangent bundle of this homogeneous space with this symplectic form. And I can go a little bit farther and really use the Marley, Guillemin, Stenberg normal form that tells me who the moment map is. So the moment map is really nice because in this associated bundle, I basically take the class of an element G and a covector here, and I simply have to send the covector to itself and let the group act, right? Still, that map can be very naughty because what do we know about these multiplicity-free Hamiltonian G spaces in general? Well, we know that indeed the orbits that we get, they are coisotropic, but almost everywhere. The map P may not be surjective and in a very bad way. So the problem with this map is that there may be points that are not interior points. And I'll show you an example later on. And also, it's true that the fibers in the image, they are almost everywhere isotropic submanifolds, that you may have points or values in the image that are non-regular. That means that if you look at the preimage, what you get is not a submanifold. And because this thing is always real analytic, it's true that you can stratify that in some manifolds, but that's telling you that there are singularities there in the system, because I mean, where you would like to have a smooth manifold, you have something which is non-smooth, and that's the kind of thing that we want to avoid. One example in which all these things that we want to avoid actually happen. Take that Gelfand pair, which is 3 copies of SO3, and take as a subgroup the diagonal guy. Don't pay attention because we don't have much time. You do the computations. There are matrices, there are vectors in R3. Consequences that I like to point out. 0 in the Lie algebra of this guy is not an interior point in the image. So if you take a point in R3 times 0, 0, and that point U is different from the origin, that point is not in the image. So the image is missing puncture-defined subspaces. So, and you have points in the image that are not clean values for the map, meaning that the preimage is not some manifold with the right tangent space. So these examples with this bad behavior exist, and we want to get rid of that. We don't want that to happen. So we're going to demand more conditions. We're not going to take ordinary Gelfand pairs. And here's the key result. So you have 3 equivalent statements, and the interesting part is that these 3 statements are of entirely different nature. So let me start by the third one, because this is a Lie theoretic statement. This is telling me that this pair, this Lie algebra and this Lie subalgebra, they are a symmetric pair. Again, whatever that means. If you don't know it, don't bother. Of maximal rank, in the sense that in the orthogonal to K, you have a maximal torus. Right? That's a Lie theoretic statement. The second statement, it has some geometric flavor, because it's telling you that if you look at the coadjoint orbits in G star and you intersect with the annihilator of K, every orbit is going to intersect, and moreover is going to intersect in a Lagrangian submanifold, which is a K orbit. And the third property, well, it's just telling you that the map is surjective, all values are clean, and all G orbits are G isotropic. And that's a statement that you can replicate in Poisson geometry because it doesn't appeal to Lie theory or anything like that. Okay? Now the names is that, well, these 2 statements are equivalent by a result of Wimber. So Wimber has a very nice review paper on multiplicity free spaces that I recommend to everyone, where he shows these 2 statements. So we proved that these 2 are equivalent to 3, but we proved it in a very unsatisfactory way, because we had to use a classification of Gelfand pairs by Mickey Duke. If you use that classification, you can check that Lie theoretic condition. And like I said, we hope we can avoid using tables or classifications, but that's what we have so far. Okay, that's my definition of a nice non-commutative integral system over a linear Poisson structure. It's going to be what we call a proper multiplicity-free realization. Proper Poisson map, such that all G orbits for the action of the Lie algebra are coisotropic. Weak submersion, P is surjective, and all values are clean. Right, so you see, this is as close as it gets to P being a submersion. If you have a submersion, all values are clean, and of course, all fibers are, if compact, they are diffeomorphic. We're postulating that the map is surjective and all values are clean. And, well, theorem, if you are in such a situation, indeed, the Lie algebra action that you had here integrates into a Lie group action of a compact Lie group, where you maybe have to change coordinates in the center. Maybe someone gave you the wrong coordinates in the center. You have to make a nonlinear change of coordinates. Maybe more importantly, there is a resolution of singularities of this guy where you can define transverse action angle coordinates, even in this non-commutative situation. So let me try to explain this point too in a very simple, in the simplest example, the only one that we can draw. So we have the following Gelfand pair, which has the right properties, is SU1 mod SO2. So the linear Poisson structure is, if you want, R3 with the concentric spheres, including the origin. So it's a non-regular Poisson structure. And on top of it, we have the cotangent bundle of the sphere. So here you have the fiber over the origin. This is a 4-dimensional thing. Pictures are not that simple, but I mean, this Lie algebra, this Lie group has dimension 1, so its orthogonal complement is a plane, is this plane. And that's supposed to be the fiber of this cotangent bundle over a given point. Now, if you take a point different from the origin, if you forget about this point about the sphere, this is nice isotropic fibration with 1-dimensional fibers. So this is one of the guys that we understand very, very well. But the problem is the fiber over the origin, okay? And I told you we can remove this singularity from P in the following way. We're going to blow up the base. So the base is this Poisson manifold that has a bad foliation because it's not singular. So you want to inflate that point. What do you do if you want to inflate that point into a surface? It's a question for students in differential topology. You can ask questions in the talk, right? You're allowed to ask questions. You would blow up the origin. So that's a very standard construction, and you replace the origin by RP2. So that gives you an honest foliation by surfaces. So you resolve the foliation, the singularity. Problem, you would like to put the same type of structure back here, so you would like to pull it back, and that be a regular Poisson structure. That's impossible, because you need to put an area form in RP2, but RP2 is non-orientable. Can't be Poisson. What you're going to do? You're going to put the zero area form. That gives you a smooth field of area forms in these spheres, and that's a Dirac structure. So again, it's a mild generalization of Poisson brackets, but it's a smooth guy, okay? Well, this works, this can be explained in this low dimension. I spoke about blow-up, but I want to do this for only algebras in more general situations, so I cannot use this language of blow-ups. I'm going to simply observe that the lines that I'm adding here, they are Cartan subalgebras for the action of SO3 for the isotropic group of the action in this point. So there's a Lie theoretic language. Rather than telling you that I'm blowing up the origin, I'm doing something of Lie theoretic nature, whatever that means. But I can do it for every Lie algebra. And I can do it in more general situations because there's a language that doesn't use Lie groups, only uses actions. That allows me to do that in more general situations. So, theorem. If you have a linear Poisson structure, this is non-abelian. That's an example of a Poisson manifold of compact type, non-regular. You can desingularize it by means of a regular Dirac manifold in such a way that the leaf spaces are the same. And for these regular guys, we know that the leaf spaces are integral affine orbifolds. So what we're saying is that the leaf space of the coadjoint action is an integral affine orbifold. That's something we know from Lie theory because that leaf spaces are mod the action of set 2. But again, this is a much more general statement. Okay. Once I told you how to resolve the base, we can also resolve the total space of the previous non-commutative integral system. So here we blew up the origin. Here we're going to blow up the central fiber in the normal directions. If you blow it up, then you are creating over each of these points a circle. And there's a very nice geometric interpretation because, I mean, if you take one of these new circles, you project into the sphere, it's going to give you a geodesic. That geodesic is the result of cutting the sphere with a plane. It has an orthogonal line. That's the point where you have to send the circle. So that's the geometric description of the map. But again, this is a description that uses the round metric. There is a description that uses Lie theory, and there's yet another description that doesn't use the language of Lie theory, so allows us to go to more general situations. Okay, let me go back. Why I claim that one can make sense of transverse action angle coordinates in this situation. You see, if I forget about the origin, I do have action angle coordinates, or when I say action angle in this situation, I really mean I have, for each Casimir, I can pair it with a function here that gives me the right part of the symplectic form. So here the radius pairs with an angular coordinate here. So those are action angle coordinates. The radius is not defined in the origin, right? So I can't make sense of that. However, if I pull it back, I still cannot make sense of the radius here, but if I pull back to the universal covering space, that's a C2 cover, I'm gonna get like the line times the sphere, I pull back the whole picture, and that the radius is well defined. What I'm simply saying is that there's a function here that doesn't make sense as a smooth function, but if you do these things, that's a smooth function in an orbifold, whatever that means. So one can make sense of action angle coordinates in this situation. And again, this guy is a submersion, right? So that's the important thing. I lost a little bit of symplectic Poisson geometry, but I improved the map. I have not much time, so a sketch of the proof of why in this situation, when I have one of these, I have the G orbits being isotropic, P being a proper weak submersion, why I can lift the action from G to the action of a compact integration of G. Well, we do that in a non-direct way. What we prove is that these two conditions allows us to build the resolution that I explained before in a very simple case. Once you have the resolution, you have here integral affine geometry in the base. I told you this integral affine geometry is extremely rigid. And working a little bit, it's telling you what is the right lattice by which you have to quotient the one connected integration to get a compact action. This is 20 pages, proof. And this is shorter, because the integral affine geometry has very nice property. But it takes some time. You see, I mean, what we're trying to do is something non-trivial. We're trying to say that the action of a Lie algebra leads to the action of a compact group. And you can think of situations in which this is not true. I mean, you have a flow, and there was this famous periodic flow conjecture that said, if I have a flow, all whose orbits are closed, then there is a common multiple of all the periods. False. Sullivan gave a counterexample. So we're trying to do something here, but the control, the conditions that we're imposing are of Lie or of symplectic nature, and that allows us to really find a compact action. How much time do I have, Nicolas?
5 minutes.
That's more than enough. Okay. To do the general case. Okay, so how do we go from linear Poisson structures to more general Poisson structures? Okay, so for that I have to tell you that some general problem or reality that we have in Poisson geometry. Now, Poisson structures on manifolds are very, very cheap. It's very easy to produce a Poisson structure. You can localize them, produce many Poisson structures. And that means that you cannot expect to have nice global theorems that explain the geometry of many, many Poisson structures. I'm not talking about results of algebraic nature, like results of Kontsevich. I'm talking about geometric results. So what do we do in general in Poisson geometry? We select special classes of Poisson manifolds in which we have specific tools. So you can work with Poisson Lie group structures. You can work with cluster algebras. And what we're doing with my collaborators is working with this kind of Poisson manifolds of compact type. So what is a Poisson manifold of compact type, in a nutshell? So you have to think of a Poisson manifold as a dynamical object. You have a Lie algebra action, and that Lie algebra is the Lie algebra of all the smooth functions. It's infinite dimensional. And that action is giving you the leaves of your Poisson structure. And you really want to control the geometry of that leaves. So you would like this Lie algebra action to be a Lie group action of a proper nature. Now this is impossible because this infinite dimensional Lie algebra, it never integrates into the action of a reasonable Lie group. But if you shift a little bit your viewpoint, you can get something which is satisfactory enough. So you really think of a Poisson structure, you go to the cotangent bundle, the bracket on functions gives you a bracket of one forms, and you have something that you call a Lie algebroid, whatever that means. That's a vector boundary with some additional structure. Now the good news is that Lie algebroids, sometimes they integrate into finite dimensional objects, which are called Lie groupoids, right? So, and these Lie groupoids, if your Lie algebroid comes from a Poisson structure, they are actually symplectic. So you have a symplectic desingularization of the Poisson manifold, where you can do symplectic geometry rather than doing Poisson geometry. This is not satisfactory enough, because if, for instance, your Poisson structure is regular, being integrable, it's only giving you constraints of how the symplectic geometry varies when you move from leaf to leaf. But it doesn't give you any control on the leaves of the symplectic foliation. And that's what we want to get. We want to get control. So what we do is we ask for the existence of an integration that behaves like a proper action, whatever that means. When you have a proper action of a Lie group, you have slice theorems. So you can start doing geometry. And that's what the Poisson manifold of proper type is. It's a Poisson manifold that has a symplectic resolution that behaves very well, gives you normal forms, gives you many things. What's the way to work in Poisson geometry to produce theorems? So, I mean, these objects, these Poisson manifolds, what they are doing is they are generalizing the following situation. So when you do Poisson geometry, and it's also the way in which people end up doing Poisson geometry, you will see a component which is symplectic geometry. So you have many symplectic geometers that end up doing a bit of Poisson geometry. You have foliation theory, because you have the Hamiltonian foliation. And you also have Lie theory. So you have these three main areas, and doing Poisson geometry is understanding the interaction. Now, each of these three areas has very nice compact objects. You have compact symplectic manifolds, you have Lie algebras of compact type, you have foliations of proper type, whatever that means. And this definition, which it's aiming to do, is to bring all these compact objects together into the Poisson category, and not only the definitions, but also the theorems. Now, how do you prove theorems in Poisson geometry of compact type? You go to a statement of symplectic geometry, foliation theory, or compact Lie algebras, for instance, of compact Lie algebras, and you try to strip the statement from Lie theoretic words, and you try to see whether that's a statement in Poisson geometry. If you manage to write it as a statement of Poisson geometry, you have a good candidate to write a theorem in Poisson geometry of compact type. And that's what we have been doing here. This is a statement in Lie theory. It's a pure statement in Lie theory. I have a compact Lie algebra, and pair, they are of maximal rank. It's purely theory. Go to 1. We can encode this Lie theoretic statement, go into the cotangent bundle of G mod K, and ask in these conditions. Well, we stripped the Lie theoretic statement from Lie theory. So, definition. This is a Poisson manifold of proper type. This is a symplectic manifold. This is a Poisson map that is proper. It's a weak submersion, meaning that surjective and all values are clean. And the action, the analog of the action of the Lie algebra that we had before, has isotropic orbits. It's the same definition that I had in the linear case that I can replicate. Theorem in progress, what I showed you in the linear case, works in this more general situation. Okay? Okay, with a little bit ahead of time, but feliz aniversario, Carlos. Thank you for your attention.
Questions? Yes.
Okay, thank you for this very inspiring talk. I have many questions.
I hope I can answer one of them at least.
Now, the first thing is, the first question which we faced was that we believed that the Torres lattice on all symplectic leaves was completely integrable. You could see this for the tridiagonal, the pentadiagonal. It's also something which we saw. If you want to look at the integrals for the pentadiagonal case, you could see an explicit degeneration of these integrals to give you independent integrals in the tridiagonal case.
I see.
So the thing that we wanted to do is how, if you start off with your maximal dimension, is there an iteration, an explicit iteration, which will tell you how to go
from those integrals to the ones.
It becomes a question of degeneration. How do you, is there something guiding you? If you use your ideas where you speak about how you can mesh together the different leaves, can you do something in this case?
I think that's a problem that you're posing for me. I cannot give you a, let's say, I can give you my impression. So if I would try to do that, first of all, I mean, the total lattice has singularities, has zeros. So I would remove them from the picture, and then I would see how much of what we have, or the situation that the total lattice can be recasted in our language. Again, the kind of systems that I'm introducing have the simplest or the least possible singularities, meaning that they do come from the underlying Poisson structure. But Toda has additional singularities because even in the regular orbit it has. So I am not sure whether that's going to be the case, but certainly one has to look at that case and one has to look at Gelfand cycling under this perspective. That's all I can say at this point.
I'm just raising that there. You gave me a little hope that one might be able to do. Next thing is when we looked at the Toda on non-symmetric matrices, we proved integrability, but there was one little thing which was a thorn in our eyes, right? And that is we didn't get a complete set of angles. There was one set of angles missing. So all of the invariant theory, which we knew and could apply to the Torres case, wasn't enough to generate for us this final small set of angles.
Angle coordinates.
So there's some additional kind of structure, which it's a structure, it's an algebraic structure, I'm sure, which needs to be found. And I wonder if there is anything that you could do about it.
Well, so two things. Jumping from the symmetric, from the compact case to the non-compact case would bring additional complications. Now, I think the key to understand or to see better what happens in these degenerate cases is the integral affine structures. When you have zeros and you look at the corresponding leaf space, what you have there is not an integral affine manifold. I mean, and we don't know very well how to define singular integral affine structures. I think this problem of defining angle coordinates in some places has to do with our current inability to extend integral affine structures to some singular points. But I would look at, I think it's a matter, or the first thing I would look at is at integral affine structures, because those encode in the base the angle coordinates. They are equivalent in some sense. That's what I would do.
Okay, I have two more questions. The other is that if you look at the example of Kovalevskaya, she found additional situation of when the spinning top was integrable. And she did it in this remarkable way. She said that she looked at all the cases where the top was integrable and their evolution in time, and she saw that if any singularities arose in time, they would have to be of a specific polar type. And that enabled her to characterize. So in the cases which you are dealing with, maybe one could use the complexification of the problem to identify interesting integrable systems. This is a possibility which I'm just raising. This whole observation of Kovalevskaya really opened up the road to Fernandes functions and things like that.
Okay, I'll
That's
noted, duly noted.
a final one, which is the one which bugs us more than anything else. And this is a problem which we address to all our numerical interests. And that is that if you look at eigenvalue algorithms, QR, Coda, how can you use all the additional integrals to get a better numerical procedure? Does it help in any kind of way? Computing the eigenvalues, you've got all these integrals, and you use them. So that is
Yeah, but that's a very general question. Is about when you look for integration methods, try to incorporate as much as the geometry as you have. Which
so
that would be the.
It's a little like this: you're sitting with a big pile of money, and you don't know how to spend it.
Okay, so you heard Carlos?
Yeah, we must do mathematicians, right?
Because you see, with Carlos, our work in the total lattice, it's very particular in the following sense. So we're trying to do as much as we can using leaf theory without using symplectic geometry.
Yeah,
So that was our goal, like symplectic geometry free. But I think we reached the point in which we have enough understanding and we have to start seeing how the two viewpoints talk to each other.
yeah, personally, my point of view is this.
What?
Numerical analysts are very lucky.
Yeah.
They got all these things in the background for free.
Yeah.
All the conserved quantities are there, right?
Yeah.
Right? They don't know it, but they are there to help, right?
Yeah.
So,
Yeah. Everybody has a fairy godmother. They don't even know.
yeah, I have a question. In what sense do you define Dirac manifolds? Do you define it in the sense of tag Dirac?
No, I define it in the. If you have a Poisson structure or even a symplectic structure, so the Poisson structure is the symplectic structure is given by a two form. The Poisson structure is encoded by a bivector. What you do to see them on an equal footing is that rather than working in the tangent bundle, you work in the sum of the tangent and the cotangent bundle.
Yeah, that's the tag law.
That's it. So you see them as a graph, and those are graphs which are very, very particular because there is a bracket in this generalized tangent bundle, which doesn't satisfy always Jacobi identity, but it does satisfy in some graphs.
Yeah.
Symplectic,
Yeah,
Poisson, and exactly. And if you have one of those guys, you call it a Dirac structure. So you're putting things together. So yes, it's in that sense, exactly.
Okay, let's thank the speaker again. So we have a very short break, and then we have a last report.